Bismillahir Rahmanir Rahim. Lecture number 16. The wave speed on a stretched string. Up till now we have discussed about a relation between the phase speed and the frequency and wavelength of the wave, but we have already discussed that the relation v is equal to f lambda does not determine the speed v, but rather it is a relationship of lambda and f in terms of v, while the speed of the wave depends favorably on the properties of the medium through which the wave travels. So, for example, if we have a stretched string, so the particles of the mediums are connected with one another, and as the wave passes through it, so each part of the string attracts every other part of the string, that is, every part exerts a force on its neighbor parts, and that force is equal to the tension in the string. Now, as we see that if there is more tension, every neighboring portion of the string will exert more force or more pull on the other part, and as a result the wave will propagate faster through such a string. So means that the speed of the wave depends on the properties of the medium, and we have to analyze these properties in terms of the Newton's second law to determine the wave speed. So the first property that we can consider is the tension in the string. Similarly, for the same tension, if we have different strings, so the inertia of the strings, how the inertia will respond. Apparently, if we have a heavier string, so it is difficult, heavier means of greater density, so the heavier string will be difficult to move up and down. That is, it has more inertia as compared to a lighter string. So means that the inertial property limits the speed of a wave on a string. So if we take into account these two properties, that is the tension in the string and the inertial property of the string, so we can arrive at some result about the speed of the wave along that particular string. If the string is uniform, so its linear mass density will be the same for all elements, and the linear mass density of the string can be determined by dividing the mass of the string on its length. So this mu represents the linear mass density, mass per unit length of the string, and we can say that the speed of the wave is somehow directly proportional to the tension in the string. We represent the tension in the string by the force F and the linear mass density of the string by the symbol mu. So the speed of the wave is directly proportional to some power of f, that is f to the power a, and it is inversely proportional to mu to the power b. We cannot say exactly that what the value of a and b should be, but if we use the dimensional analysis, we can determine the values of a and b, and we can establish a relationship of the phase speed in terms of the tension and mu of the string. So let us write the dimensions of the left hand side and the right hand side. This is the dimension of the speed, mass. This is L is the length, distance per unit time, and the force is kilogram meter per second square to the power a, and this is mass per unit length to the power minus b, as here is the power b in the denominator. So if we write it in the numerator, its power will be minus b. Now rearranging these quantities, we see that L into t to the power minus 1 is equal to m to the power a minus b, L to the power a plus b, and t to the power minus 2a. Now comparing the powers of each of these dimensions, we can determine the powers of a and b. So comparing the dimensions of the powers of t, on the left side the power of t is minus 1, and on the right side it is minus 2a. So minus 1 is equal to minus 2a, which implies that a is equal to 1 over 2. Over here, if we compare the powers of L on left and right side, so on left side the power of L is 1, while on the right hand side the power of L is a plus b. So we get 1 is equal to a plus b from the above. Over here we have a is equal to 1 over 2, so b is equal to 1 minus a, 1 minus 1 over 2 is equal to 1 over 2. So we have determined the values of a and b which we need. If you go for the third dimension, that is of the mass, so on left side there is no mass, that is m to the power 0 over here. So 0 is equal to a minus b, that will give you a is equal to b, which is half. So finally we can write the above formula. V is proportional to f to the power 1 over 2 divided by mu to the power 1 over 2, or V is equal to some constant into f over mu under the root. This constant should be dimensionless, and this is a proportionality constant. Later on we will see that this constant is equal to 1. This was the dimensional analysis on the basis of which we arrived at an equation V is equal to C into F over mu under the root, but that was not a proper derivation of the equation for the speed of the wave along the string. Now let us mechanically analyze and rigorously derive a relationship for V in terms of F and mu of the string. So to do this, let us consider a snapshot of the wave pulse that is moving to the right along a stretch string with a speed V. Equivalently, we can say that the wave pulse is stationary and the string is moving to the left with the same speed v. Now consider a small section of the pulse with length delta L. This portion, let us consider this portion between these two lines, that is the top portion of the pulse. It has a length delta L. This section is approximately a section of a circle with radius r. So it is an arc centered at this point with radius r of a circle. The mass of the element is equal to delta m, and that will be equal to mu times delta L, where mu is the linear mass density of the string. The tension force in the string is tangent to each end of the element. At this point, the tension force is directed along the string. So if we are taking just at this point, this is in this direction, while on the right side it is tangent to this portion and is given by this. This tangent force on both the sides makes an angle theta with the horizontal axis. So with the vertical line also, this radius vector will also make an angle theta. This is simply on the grounds that if there are two lines and they have an angle theta between them, so if we draw perpendicular to both of these lines, the angle between those perpendicular will be the same as that theta. So over here you see that between F and the horizontal lines there is an angle theta. So this line R is perpendicular to this F to the tangent. Over here this R is also perpendicular to this tangent, this F, and this vertical line is perpendicular to the horizontal line. So also between this vertical line and this R, the angle will be theta. So this total angle, this arc angle, will be equal to 2 theta. Now what we can do, if we focus at this, the tension force which is tangent at this point and at this point, so look at the motion in the string. As the wave travels along the string moves up and down, that is perpendicular to the propagation of the wave, but there is no motion along the x-axis. That is, the string does not move in the direction of the wave. So the x component, the net force along x-axis will be 0. If we resolve this F and this F into rectangular components, their x components will cancel out, while the only net force that remains will be along the y-axis. Over here, if we look at this, so the y component of this force is also downward and of this force is also downward. So both of them will add up, and if we take a single triangle of the force, so this is the force that tension force. This is the horizontal component of the force, and this is the vertical component. The horizontal component is F cos theta and the vertical component is F sin theta. Similarly for this one, but for these two forces, these two tension forces, the tension force at two different points, or the x components are oppositely directed, and as there is no motion along the x-axis, so they cancel out, and the net force along x-axis is 0, but the y component is F sin theta for one, and similarly F sin theta for the other side as well. So the net force along y-axis comes out to be 2 times F sin theta. This one. If this angle is very small, when we say, often we use the relation that the approximation that F theta is small, so sine of theta is approximately equal to theta. But how much small? This small means that much less than 1 radian. So if the angle is very small, we can use this approximation that sine of theta is approximately equal to theta, and we can call this relation as 2f theta. Now, what is theta in terms of the r and length of the arc? So we can see that 2 theta is equal to delta L over r. Thus we have Fy, the net tension along the y direction, is equal to 2f theta and equal to f into delta L over r. Delta L over r is for 2 theta, and this is actually the force that provides centripetal acceleration to the particles of the string. And that for centripetal acceleration, we know that the relation is v square divided by r, where v is the speed. So the tangential velocity v up the top of the element is horizontal and is equal to the wave speed in magnitude. Applying Newton's second law to this element of mass delta m, we can write the net force Fy is equal to delta m into Ay, as we know that F is equal to ma according to the Newton's second law. This Fy, according to this equation 3, is F delta L over R, where F is the tension in the string. So this is delta m into v square r. We have replaced Ay by v square r for the centripetal acceleration. So now from here we can see that F delta L over R is equal to as delta m, mass is equal to mu times delta L, and this is v square over R. So we can cancel delta L on both the sides, and R, and we are left with F, the tension, is equal to mu times v square, where v is the wave speed. So v square comes out to be F over mu, or v is equal to F divided by mu under the root. Now from here we can see that the constant c that we have used in the dimensional analysis is equal to 1 from this relation. So this is the wave speed, and it only depends on the tension in the string and its linear mass density. That is, these are purely the mechanical properties of the medium, and the frequency of a periodic wave is always the same as that of the frequency of the vibrating source where the wave travels through. When the wave travels through a medium, the speed v of the wave is determined by the properties of that medium. And as, for example, in the above relation v is equal to f over mu, we see that if we replace the string by another string which have a higher tension, so the speed in this string will be more than the previous one. So the speed v is determined only by the properties of the medium. Now if we connect two strings to each other like this, and we allow a wave that passes through this string, the left side of the string, with speed v1, and in the right hand side, in the red one, the string, the speed is v2. These two strings have different linear mass density, mu1 and mu2, and due to that the speed of the wave will also be different in these two media. But remember that the frequency of the wave will not change. So what will happen if, suppose we have this mu1 smaller than mu2, and let the tension is the same in both the strings, so then v1 will be greater than v2. What will happen to the wavelength? As we know that v is equal to f lambda, where f is the frequency of the wave. So this relation. So what will happen? F will remain the same in both the string. It means that lambda will change. So how the lambda will change? We can have the same frequency f in this string as well as in this. So f in this string will be equal to f in this string. The frequency, and f means frequency here, the frequency here is equal to v1 over lambda 1, and in this string the frequency is v2 over lambda 2. So over here we have that v1 over lambda 1 is equal to v2 over lambda 2. It means that if you have two different media and an interface between these two media, if the wave travels through one medium and passes through the interface into the other medium, so the relationship of the wavelengths and speeds in the two media will be v1 over lambda 1 is equal to v2 over lambda 2.